In this video, we're going to continue our look into trigonometric identities, deriving some useful relationships between sine and cosine, along with determining what happens if we find the sine or cosine of a negative angle. So allow me to start out by drawing a right-angled triangle here on the whiteboard. So I'm going to mark the angle that's 90 degrees, the right angle, and I'm going to name our other two angles, one as alpha, and the other angle up here I'm going to name as beta. Now we know in any triangle the three interior angles of that triangle add up to 180 degrees or pi radians. Therefore in our right angled triangle here we know that alpha plus beta plus our right angle, which is 90 degrees, add up to 180 degrees. If I was to subtract 90 degrees from both sides of this equation, we see that alpha plus beta equal 90 degrees, which is also equal to pi over 2 radians. Now, the fact that alpha and beta add up to 90 degrees means they are called complementary angles, because any two angles that add together to make 90 degrees or pi over 2 radians, that's what they're called. They're called complementary angles. So alpha and beta are complementary angles. The fact that alpha and beta, the two angles in our right-angled triangle other than the right angle, the fact that they're complementary angles actually is going to allow us to show some useful relationships between the sine and cosine trigonometric functions. To do that, I'm going to need to apply our sine and cosine trigonometric ratios to our right-angled triangle. And that means I'm going to need a way of referring to the edges in this triangle. So I'm going to call the edge that's opposite our right angle, which we know is our hypotenuse, I'm going to call that H. I'm going to call the edge that's opposite alpha as A, and the edge that's opposite beta as B. So we've got our two trigonometric ratios, our sine and cosine ratios, and we know that sine of an angle is equal to the opposite over the hypotenuse, and that cosine of an angle is equal to the adjacent over the hypotenuse. So if we apply these to our right-angled triangle, hopefully we can see we're going to get four different relationships. We're going to have sine of alpha, sine of beta, cosine of alpha, and cosine of beta. So let's write those four relationships now. So sine of alpha is equal to the opposite over the hypotenuse. Well, the opposite of alpha is A, and our hypotenuse is H. Scroll down a bit. The sine of beta is equal to the opposite over the hypotenuse. The opposite of beta is B, and the hypotenuse is H. The cosine of alpha is equal to the adjacent over the hypotenuse. Well, the adjacent to alpha is B, and the hypotenuse, of course, is H. And the cosine of beta is equal to the adjacent over the hypotenuse. Well, the adjacent of beta is A. And again, that's over our hypotenuse, which is H. So if I was to scroll down just to look at these four relationships, you'll see two of them are equal to A over H, which means that sine of alpha is equal to the cosine of beta, and two of them are equal to B over H, which means that the cosine of alpha is equal to the sine of beta. So we can say the sine of alpha is equal to the cosine of beta, and the cosine of alpha is equal to the sine of beta. But why is this useful to us? Well, we said earlier, alpha plus beta add together to make 90 degrees, or pi over 2 radians. So if alpha plus beta equal 90 degrees, well then we can write alpha in terms of beta. If we take beta from both sides of the equation, we can see that alpha is equal to 90 degrees minus beta. So if we take this value that we know alpha is equal to and substitute it into both of our equations here, we can see, if I scroll down to give myself some room, that the sine of alpha, which we know would be the same as the sine of 90 degrees minus beta, so the sine of 90 degrees minus beta is equal to the cosine of beta. And the cosine of alpha, and we know alpha is 90 degrees minus beta, so the cosine of 90 degrees minus beta is equal to the sine of beta. So what you'll notice, if I scroll down just to focus on these two equations, what you'll notice is that these two equations are only referring to one variable, beta, in each case. So that variable is just an angle. It doesn't really matter now how it relates to that right-angled triangle. It's simply just an angle. And that allows me to write this in a generic form that doesn't relate to the diagram that we showed earlier. And that generic form is that the sine of 90 degrees minus an angle theta is equal to the cosine of that angle, and the cosine of 90 degrees minus an angle theta is equal to the sine of the angle theta. We could of course write this in radians, so we could say the sine of pi over 2 minus theta is equal to the cosine of theta, and the cosine of pi over 2 minus theta is equal to the sine of theta. Now these two equations are known as the complementary angle identities, and they're helpful because they can allow us to convert between the sine and cosine of an angle. Now these particular identities are the kind of relationship that might not in and of itself be directly applicable to a problem. However, as they are quite simple and thus they don't take a long time to explain, and because they do crop up quite a bit in more advanced trigonometry, much like our Pythagorean identity does, I wanted to cover them on this DVD so that you have a good idea, a good understanding of why these identities are true, where they come from, and how we can prove them using our right-angled triangle. And that way, if you continue your studies into more advanced trigonometry, and you may encounter trigonometric proofs that make an assumption such as the sine of pi over 2 minus theta equals the cosine of theta, and it will make that assumption, and you may, if you didn't understand where it comes from, you may be left wondering, well, how is that equal? How is that true? But now you know where it comes from, you know that's true, and you can see where they're getting that proof from. The other set of identities I wanted to look at in this video are identities that relate to what happens when we take the sine or cosine of a negative angle. Now again, whilst they're not necessarily very useful on their own, they are useful when we start to find more complicated trigonometric relationships, as we'll see in the next video. To derive these identities, it's actually easiest to use the unit circle. So I'm going to bring up a unit circle that I created earlier. Fantastic. And we've already seen, we know that a rotation from the x-axis in the anti-clockwise direction is a positive rotation. So if we call this rotation theta, we know that theta is a positive value. It is a positive rotation. So any rotation that's going anti-clockwise is positive. Well, a negative rotation, a rotation of a negative angle, is simply a rotation in the opposite direction. Therefore, it's a rotation in the clockwise direction. So if we rotated by minus theta, that is to say a negative rotation of theta, we'd rotate through the same angle, we'd simply just rotate in the opposite direction. So if we were to rotate through negative theta, we'd get something that looks a little bit like this. So we'd rotate through the same angle, only it's in the opposite direction. So if theta equaled 45 degrees, for example, this would be minus 45 degrees. It's the same magnitude of the angle, it's just in the opposite direction. Now you notice as theta increases, rotating us further and further anti-clockwise, negative theta is going to decrease, rotating as clockwise, but it's going to decrease at an equal amount. That is to say, these two lines that are defined by our rotation are always going to move by the same amount, which means they're always going to be a mirror image of each other, if you will, about our x-axis. So no matter how far we rotate, these lines are always going to be a mirror image of each other. If we're rotating by positive theta in one direction, and that moves us, say, to here, negative theta is going to move us by the same distance, which means our line is going to be a mirror image of the positive rotation. Now this is interesting because we can think about the endpoints of these two lines, the endpoint that sits on the circle, in terms of their x and y coordinates. We've already seen when we're dealing with just a positive rotation that we can name these coordinates of that point as x, y. Will allow me to name the coordinates of the point where we have a negative rotation as x dash, y dash. So they're just another set of coordinates. They have a different set of values to x and y. Well, what do we know about the relationship between these coordinates? Well, we can see that our x coordinates are always equal. No matter how we rotate these two lines, because they're a mirror image over our x-axis, they're going to have the same x coordinate. We could see if we were to rotate to bring our positive rotation line over to here, our negative rotation line would rotate through the same amount but in the opposite direction. And we can see again that these share the same x coordinate. We can see this even if we rotate past 180 degrees. If we rotated all the way around, say, to here, well, then our negative rotation would be the same amount but in the opposite direction. That would give us something like this. And again, my diagram's a little off here, but if these were the same rotation, they'd share the same x coordinates. So what we can say in general terms is that x dash is equal to x. That is to say, the x coordinate of our negative rotation is equal to the x coordinate of our positive rotation. But what about the y coordinates? Well, you'll notice already that our y coordinates here, even though they share the same x coordinate at points, our y coordinate, one of them is positive and one of them is negative. Now we could prove, I'm not going to do it, but we could prove through Pythagoras' theorem, because we know each of these lines is a length of 1 and we know the x coordinates are the same. We know the length of the y part of a right-angled triangle here would be the same. They have to be the same. If these two edges are the same, these must have the same length. I'm not going to go through the full proof, but you can hopefully follow with me that indeed the length or magnitude, if you will, of the y coordinate is the same, but one of them is positive and one of them is negative. This is the same for any rotation. So if we were to rotate, say, to about here, our negative rotation would bring us down to about here. You can see again, one y coordinate is positive, one y coordinate is negative. Even if we were to rotate past 180 degrees, bringing us, say, down to here, we know our negative rotation would be the same amount but in the opposite direction, giving us something like this. And we can see one of our y coordinates now, our positive rotation's y coordinate has become negative, but as soon as this guy becomes negative, our negative rotation's y coordinate becomes positive. So what we can say in general terms is that y dash, as I scroll down a little bit, y dash is equal to minus y. So this is to say that the x coordinate of a negative rotation is equal to the x coordinate of a positive rotation, but the y coordinate of a negative rotation is equal to minus the y coordinate of a positive rotation. Now we can extend this concept further. Near the beginning of this DVD, we used our x and y coordinate to define sine and cosine. So therefore we know with our positive rotation, a rotation of theta, we know the following is true because we use this to actually define sine and cosine. We know that x is equal to the cosine of theta, and we know that y is equal to the sine of theta. Well, if x is equal to the cosine of theta and theta is positive, x dash is going to be equal to the cosine of our negative rotation. So x dash is equal to the cosine of negative theta, and likewise y dash is equal to the sine of negative theta. We can see this if we use x and y to define the cosine and sine of this rotation, and our negative rotation has given us these coordinates, then surely the sine and cosine of that negative rotation are equal to those coordinates. And in fact, yes, they are. It's exactly how we've been defining cosine and sine. So now that we have these four relationships, we can use them to replace x dash, y dash, x and y in these two equalities. So x dash, which is the cos of minus theta, so the cosine of minus theta, is equal to x, which here we know is the cosine of positive theta. So the cosine of minus theta is equal to the cosine of positive theta. Here we have y dash. Well, y dash here is equal to the sine of negative theta. So the sine of negative theta is equal to minus, so minus, that is important, y here is the sine of theta. So it's equal to minus sine theta. So here we have two identities. We have the cosine of negative theta is equal to the cosine of theta, and we have the sine of negative theta is equal to minus the sine of theta. These two identities are our negative angle identities. Now we can actually extend this further to see what happens when we find the tangent of a negative angle. Earlier we defined the tangent of an angle, and we saw this defined in terms of sine and theta. We saw it's equal to the sine of an angle divided by the cosine of an angle. Therefore, the tangent of a negative angle is going to be the sine of a negative angle divided by the cosine of a negative angle. Now, I'm not going to scroll down here just so we can actually see our relationships up here. So we saw the sine of a negative angle is equal to minus the sine of that angle, so minus sine of theta. And we saw the cosine of a negative angle is the same as the cosine of an angle. So this is equal to the cosine of theta. Fantastic. So we can see, oh, I scrolled a little too far because I want to relate it up to here. So we could write this as the tan of minus theta is equal to, I can bring this negative and I can simply put it in front of our fraction. So it's equal to the minus of sine theta over cosine theta. Well, sine theta over cosine theta is tan theta. Therefore, tan of minus theta is equal to minus tan theta. So our third negative angle identity is that the tan of minus theta is equal to minus the tan of theta. So that is our third negative angle identity, and it comes from the fact that our cosine and sine behave in this way. Our cosine of a negative angle is equal to the cosine of the positive angle, but the sine of a negative angle is equal to the negative of the sine of the positive angle. So hopefully you all agree that the identities shown in this video are all very simple, and they're very clear, very easy proofs. Therefore, I don't feel personally that there's any need to test the knowledge that we've covered in this video. However, as I mentioned earlier, whilst all of these identities are very simple, and whilst they might not seem particularly useful for direct application to problems, they do form a series of relationships between our trigonometric functions which can help us when we're deriving or proving more complicated trigonometric identities. So although we might not make much use of these identities in this DVD, or we might not discuss any of the truly complicated trigonometric identities on this DVD, by showing these proofs for these simple identities which are so often overlooked in mathematical texts. So often you'll just see these stated, or you'll just see our complementary angle identities stated, and you won't actually see the proofs for them. So often they're overlooked. But hopefully, so that you now understand where they come from, it's going to help you in your future studies into more advanced trigonometry, because you'll have an understanding of where they come from, what they mean, so when you see people using them to prove more complicated trigonometric relationships, you'll fully understand what that particular mathematician is doing, and it won't look like they've just grabbed some identities out of thin air. So I hope you have enjoyed this video. Thanks a lot for watching, and I'll see you in the next video.